Good morning to all of you. In this lecture, we will discuss about the islanding detection of microgrid system, and we will just cover the passive islanding detection technique. First, we will see what is a microgrid. We will see when we just connect different types of renewable sources like solar, wind, or even also battery storage system to a distribution network, that particular area is called as microgrid. It is a self-sustained system where the generators and loads are present, and also sometimes this microgrid operates either in grid connected mode or in islanded mode of operation. What are the advantages of microgrid? Basically, it has electricity peak demand, energy efficiency, active customers in the renewable energy revolution, line cost, system reliability, and so on. If you see all these advantages which are concerned with the microgrid system, and that is why we are interested for smart grid environment. And in fact, we have integrated solar, wind, fuel cells successfully to our distribution network, even to some extent in the transmission system also, or transmission network. And also we are planning to have 100% renewable integration in our network. Now, that is the reason, I mean these are the points why we are interested for renewables or smart grid system. This is very important that the energy crisis and environmental issues like carbon dioxide emission, as our production, our energy consumption comes from the coal based generation system and mostly 60%. So, obviously carbon dioxide emission is one concern. So, reduce that particular carbon dioxide emission process, we have to generate more power from renewable sources like solar, wind system. And also these sources are environmental friendly, because as we do not have this carbon dioxide emission process, so it keeps the environment neat and clean. And of course, for propagating this encouraging people to have access or to have generation from these renewable sources, the government is also providing incentives, and a lot of schemes are also going on, like in R&D activities or in government level different types of schemes are coming to basically encourage people to have this renewable sources at their premises. If you will see this particular PPT here, the operation of the grid may be in grid connected mode of operation, where the microgrid is connected to the grid system or main supply or main substation, we can also call it, and also it has this islanded mode of operation. The microgrid can also operate in islanded mode. Islanded mode means when the main grid is disconnected due to certain fault at the main grid side, then the microgrid system will operate in a islanded mode. Also we have transition to island and reconnection modes. Transition to island and reconnection modes, if it is islanded, I mean if the microgrid is islanded from the main grid, again this island can be connected to the main grid system. That is basically known as restoration process of the smart grid system or microgrid system. So, that is why based on this different mode of operation of microgrid or smart grid system, basically obviously we are interested for islanding detection mode of operation. When this particular microgrid system is islanded, and we have to basically detect the status of this microgrid, otherwise the system will be in trouble or different types of difficulties will arise. So, we will see what are what is this islanding system and what are the consequences of this particular islanding system, we will discuss in detail. First of all, we will define this islanding word. What do you mean by this islanding? According to IEEE standard, a condition in which a portion of an area electric power system, that is EPS, is energized solely by one or more local EPS through the associated PCC, that is point of common coupling, while that portion of the area EPS is electrically separated from the rest of the area EPS. This particular statement you will understand from this particular two figures. These two figures will make us understand that what is this islanding basically. In simple word, if you see this left side figure, this is our grid, this is our main grid, and this particular system is our microgrid. And this main grid and microgrid are connected together through this PCC, that is a point of common coupling. And if you could see here this microgrid system, we have wind, we have PV, that is photovoltaic or solar system, and also we have batteries for the storage purpose, and also we have EV, electric vehicle, flywheel also for the storage, and of course we have like household appliances like consumer loads, and together basically this particular network is known as microgrid, and this microgrid is connected to the main grid through this point of common coupling. If this point of common coupling due to certain fault at the main grid side, if the main grid is basically isolated or disconnected from the the microgrid using some circuit breaker system, obviously at that time this microgrid is going to be islanded from the main grid. That means the microgrid is not anymore connected or not anymore getting power from the main substation or main supply. That is what the meaning of this islanding. Some portion of this microgrid system is islanded from the main grid. Our main grid is not supplying power to the microgrid. That is known as islanding of the system. And even the second figure also says the same thing, that we have here source 1 means this is the main grid. This source 1 is our main grid, and this main grid is connected to the microgrid with help of B1. B1 is the circuit breaker. We are naming this main grid side breaker as B1. B1 is the main grid side circuit breaker. This source 1 or the main grid is connected to the dotted line. This dotted line shows our microgrid system, where we have this solar, and also we have synchronous based DG, and also we have like here one solar. Yes, of course we can add the wind system also and loads. Now together this solar, wind, battery or synchronous based DG's loads constitute the microgrid system, and this total microgrid system is connected to the main grid with help of this circuit breaker B1. Let us say due to some fault, if this at the grid side, if any fault is incepted, now the circuit breaker B1 is basically going to be opened, otherwise this fault current will penetrate to the microgrid system and it will damage the other equipment which are present inside the microgrid. So that is why we have to disconnect the faulty section, basically the main grid system, from the microgrid, and this operation is known as islanded mode of operation of the microgrid system, and this condition situation is known as islanding. We have different types of islanding depending on the system structure, or you can tell it connection, or you can say the planning of the system also decides different types of islanding, in what manner this system is present. If you could see here, this is known as the partial feeder microgrid, because all the feeders are not present here. And if you could see here, we have like full feeder microgrid. Here all the feeders, if you could see the inside box, this one is basically the full feeder microgrid system. Let us say due to certain reason this particular breaker is open, so that means the total full feeder microgrid is now isolated from the main grid, and this is our main grid. This is a bulk supply generation or substation, you can say. And we have also single customer microgrid. Single customer microgrid means we have a single customer, and near to the customer end we have DERs, like distributed energy resources, which are supplying the power to the customer. Now if this particular breaker, if you could see here, if this particular breaker is open, now this single customer microgrid system is going to be isolated from the main grid. And similarly, if this particular breaker, if you could see here, if this breaker is open, now the partial feeder microgrid system is going to be isolated from the main grid. Depending on the structure or planning or layout of the distribution system or distributed energy resources network, then different types of islanding is going to be appeared. Now, what are the consequences? Why you are so much interested to have this knowledge about this islanding status, or I can say in other word, we have to basically detect the islanding mode of operation of the microgrid system. Why it is so much necessary? Why it is necessary? Or we can say what are the consequences if you are not going to detect this islanded mode of operation? The first one is it will cause out of phase reclosing. We have the main grid, and this main grid has certain voltage and frequency, and similarly we have the microgrid system where we have synchronous based DGs, and we have solar based DGs, and also we have wind based DGs, and that particular microgrid system has certain frequency. And when these two frequencies match, then only we can synchronize and the system will be stable. If the two frequencies basically do not match, then the system will be in unstable mode, and that is what during the islanded mode of operation, the frequency of islanding system may be different than the frequency of our grid system, because in islanded mode of operation it is not necessary that the loads which are present inside the microgrid is exactly matches with the our generation which is present inside the microgrid. In other word, I can say that the number of loads or load which is present inside the microgrid should match perfectly with the generation, then only the frequency will remain stable, the frequency will be stable, otherwise the frequency will vary. If the load does not match with the generation, then frequency will vary. Basically the active power, I am talking about the active and reactive power part. So, that is why this due to the frequency mismatch, this out of phase reclosing issue comes to picture. Second one is the degradation power quality, as already we discussed that the frequency and voltage change with this islanded mode of operation, and that is what the basically the power quality issue. The frequency does not remain at the nominal value and the voltage does not lie within this limit. So, obviously we will call it as a power quality threat due to this islanded mode of operation of the microgrid. And also we have grid protection interfaces like different types of relays, reclosures, fuses we use. So, those protection equipments may maloperate during this islanded mode of operation. Then we have the inverter control mode switching, because inside this microgrid we have solar, wind system. So, those equipments like energy resources use the inverters. So, this inverters have some control strategy, and if this system is islanded, if the microgrid is islanded from the main grid, so that means the PCC voltage frequency are going to be changed. And it is to be mentioned that the control strategy which is running inside the inverter of the different types of renewable sources, the inverters, the control strategy takes the voltage and frequency feedback from the point of common coupling. In that case, if the frequency and voltage of the PCC change, so obviously the input to the controller of the inverter are going to be changed. That is why this inverter control mode switching may happen. I mean, this controller may go to some other mode of operation. Then we have we have discussed this small functional protective devices and equipment damage, and if suppose if you are not going to shut down some DGs, then of course we will have some issues like if it is basically a synchronous based DG, and the rotor will experience certain kind of damage issues. Threats to personal and crew man safety. Yes, this is also important point, because if suppose some loads which are connected at the grid side, and the people who are working the grid side, and this our microgrid system is disconnected from the main grid, but the notice is not given to those crew person that already the power is not coming from the main this microgrid system, but however they are getting power from the main grid. The system is like this. This is our main grid, this is our circuit breaker, this is a point of common coupling, and this is a circuit breaker for the DG. We can name it DG, distributed generation, or we can name it also DER, distributed energy resource. And this is our main grid. This is our main grid, circuit breaker B1, and this is B2. Due to certain fault, if this circuit breaker B1 is out of service, it is basically open, basically not out of service, it is basically open to just clear this particular fault, so that the fault current should not penetrate to the rest of the microgrid system. And what will happen, let us say few loads are here, and those loads are basically the utility side loads or main grid side loads, and these loads will get supply with help of the DG, which is present inside my microgrid system. This is a very schematic, very simple diagram I have shown here to say that how this threats to the personnel or crewman occurs due to this particular islanding of the microgrid system. And if this information is not present to this crew person, then obviously they will get some shock. Now, these are some of the consequences or difficulties which are associated with islanding detection issues if we are not going to detect this islanding mode of operation of the microgrid. So, these problems are going to occur. And above all, we are thinking for the smart grid system. In this particular slide, we will discuss again that why this islanding detection is very, very essential. That we have this smart grid environment where we are looking for central controller or local controller, and this central controller will gather all the information from all the circuit breakers, all the renewable energy sources or loads from every corner of this microgrid or smart grid system. The central controller will collect all the data. Now, if of course at any time suppose there is some fault, there is some difficulty, some disturbances, then this particular central controller will take care. Then it will just initiate some trip signal or initiate some control action signal, and it will just actuate corresponding devices which are present inside the microgrid or smart grid system. Now, the point here is, if let us say one of my renewable energy sources is basically, if one of my renewable energy sources is disconnected from the main grid or from the microgrid system, and that particular status, the status of this particular circuit breaker should be sent to the main control station, where the controller will take some decision. And more clearly, I will just come to the correct point, like straightforward point, like that is during the protection coordination of the directional overcurrent relays, we have to basically know whether the system is islanded mode of operation or the system is in grid connected mode of operation. So, in that case what will happen, if you do not know what is the mode of operation of the system, then obviously we cannot adopt our technique, we cannot adopt or we cannot change our technology, I mean the protection philosophy. So, change the philosophy, protection philosophy, we have to, of course, we have to know the mode of operation of the microgrid, whether it is connected to the grid or whether it is not connected to the grid, whether it is connected to the one feeder or the switch circuit breaker is disconnected. So, all the information we need. So, in that case this islanding detection is must. The island detection algorithm or technique basically will detect, and it will just send the message to the central controller that this particular area or this particular microgrid is disconnected from the main grid, or we can say these are the distributed energy sources which are disconnected from the circuit. So, those information are very, very essential at the central controller section, where we are going to take the final decision. Now, for this islanding detection, one factor, one point, the power mismatch is very, very important. If you could see here that let us say this is basically the grid, the main grid, and this is one renewable energy source, this is second, the first, and this is the second renewable energy source. and these are my loads, load 1 and this is load 2. Due to certain reason, this grid is now disconnected. So, rest of the microgrid system is now islanded. It does not mean that during the islanding mode of operation, this P load is equal to PDG, not necessary. So, that particular condition is known as power mismatch condition, whether my this QL is equal to QDG or my P load is equal to PDG. Is it possible? It may not be possible. And also sometimes it is also possible, it may also happens that this load P load is equal to PDG also. Perfectly power mismatch condition, it is known as perfectly power mismatch condition. And also sometimes it may happen that this QL Q load is equal to QDG. So, it depends on the operating mode of operation of the microgrid system, how many loads are switched on, how many loads are switched off, how many DGs are working condition, how many DGs are off. So, it depends on the system operating condition. So, based on that we can say whether this PL is equal to PDG or QL is equal to QDG or not. If suppose this PL is not equal to PDG, then what will happen? This PL minus PDG, that is our delta P, the active power mismatch. And just I have shown here, you could see here that del P is equal to PL minus PDG, that is P grid, and this del Q is equal to P load minus QDG, the difference between the load reactive power and the DG reactive power. So, these are the terminology I just written here, what are the words, the definitions. Now, the question comes, why this power mismatch is also important as far as the islanding detection is concerned. We will discuss in this particular figure. Let us say this is basically known as NDZ. NDZ means non detection zone. This NDZ is defined that for what particular percentage of power mismatch the islanding relay does not detect the islanding condition. Very simple sentence, very simple definition. This NDZ is defined as the percentage of power mismatch for which the particular islanding relay does not detect or it is not able to detect the islanding condition. So, that particular situation is known as NDZ, non detection zone. What is this percentage of power mismatch? Del P percentage, we have also del P, del Q percentage, the active power mismatch percentage and the reactive power percentage, mismatch percentage. Sometimes we start with call it 0% power mismatch. What is the meaning of that? At that condition the load P load is equal to PDG. That means there is no difference between the load and the generation. So, that is known as 0% power mismatch, active power mismatch or 0% reactive power mismatch. If it is 10%, let us say plus 10% del P. So, what is the meaning of this? If it is plus and also minus, so both the cases it has certain meaning. If it is plus 10%, that means our PL is greater than PDG. This is very very important when you design, basically we develop some detection algorithm to detect the islanding mode of operation of the microgrid. If suppose this is minus, if it is minus 10% P del P, then what is the condition? It is like this, PL is less than this PDG, right. So, these are very important points we have to basically will follow in the next class what are the impacts of this particular power mismatch conditions on the algorithms, the island detection algorithms. Coming to this particular NDZ picture, along the x axis we have delta P, plus delta P, along this negative axis we have this minus delta P, and here we have plus Q, here we have minus delta Q. Now, if suppose this delta P is higher, that means it is load power is more than the DG power. So, that means it is the system is loaded. the voltage is going to be reduced. So, we are here our under voltage relay, this UVR means the under voltage relay is going to experience some trip signal. Now, similarly for this case, if you have this del Q, your load is more, Q load is more, then this frequency relay under voltage under frequency relay is going to be actuated, and similarly for the other two conditions. Now, according to this IEEE standard, IEEE 1547 standard, basically during islanding we have certain standards, we have to follow it. What are the standards? What is the status of the frequency? What is the status of the voltage? What is the time required to have to take some decision? And remember, we are talking about this islanding, which is basically unintentional islanding condition. You know, the islanding is basically two types, unintentional islanding and intentional islanding. So, we are talking about the unintentional islanding situation. So, where this if any islanding situation occurs, so we have to basically trip the DGs, the distributed generations or the distributed energy resources. And in case of intentional islanding, intentionally we are creating some islanding mode of operation of the microgrid, intentionally we are doing it. It is not required to basically trip the DGs. You know why this intentional islanding is coming to picture? Due to the huge power demand, I mean at the customer side, now we are not ready to trip the DGs anymore. So, that is the encouragement, that is the issue basically which is coming off. We have to follow certainly this intentional islanding mode of operation of the microgrid system, that is what. Now, we are just discussing the unintentional islanding. In this particular course, we are discussing about the unintentional islanding situation, and here I will discuss what are the IEEE standard like 1547 standard for all the DERs are to be equipped with under voltage, over voltage and under frequency, over frequency relays. That is must, because when these DERs are disconnected from the main grid, the voltage and frequency are going to be changed. So, to basically detect whether this frequency and voltage are within the limits or not, so in that case the relays are the best equipment. So, the relays will decide whether the DERs are connected or disconnected. So, all the decisions we can take from those relay points. Now, this for the voltage relays, the set point is within 1.1 per unit to 0.88 per unit. Low, we have lower limit, this is a lower limit, this is the upper limit. Similarly, for the frequency relays, we have like for 60 Hz system 60.5 and for 59.3. Similarly, we have also 50 Hz system. And of course, we have different other standards. The another point I just want to mention here, this islanding detection should be within 1 to 2 seconds. So, we should not exceed more than this, that is also another point. I have tabulated all the points, what is the trip time required. Like if you could see here, this is if the voltage is below this 60, then it will, the trip time is 6 cycles, and this V is within 60 volt to 106 kilovolt. The trip cycle is time is this much. So, there are a lot of standards are available in IEEE templates, you can see it IEEE 15, this one 1547. The island detection standards are mentioned there. Now, coming types of island detection technique, one is the passive, second one is active, third one is hybrid, and the fourth one is communication based technique. In this particular class, I will discuss a little bit about this passive, the basics, what are the basic techniques which are used for detecting the islanding mode of operation using this passive technique, passive mode of operation. Passive means basically we are just estimating the parameters or signals or quantities at the terminal of the distributed energy sources, and then we are deciding whether this microgrid is disconnected from the main grid or not, passive techniques. Now, we have like very shortly just I will discuss that passive detection techniques use continuously basically monitor the electrical quantities or parameters at the terminal of the DERs. Just I discussed before 1 minute that we mainly measure this voltage or current or frequency, power source to sometimes. So, those parameters quantities are basically measured at the DG terminal to take further decision. In case of active island detection techniques, we have like inject extra signals from the outside, that is called as the disturbance signal at the terminal of this controller for the inverter to see what is the impact at the PCC voltage or frequency or power even sometimes. And hybrid means together we are adding this passive technique and active technique, and that is the name is hybrid island detection technique. In one of my class I will discuss in detail this hybrid and communication based island detection technique. And communication based island detection technique basically based on the communication infrastructure, like we have worms and also we have SCADA system. So, those communication infrastructure can be utilized for island detection purpose. Now, as we discussed that this passive island detection technique is based on measuring this quantities like voltage, current and frequency, or sometimes also we measure this power and also parameters, like also we calculate the impedance, reactance or resistance variation at the PCC bus by calculating, I mean basically measuring the voltage and current at the PCC bus. Now, we have different types of passive island detection techniques. We have power quality based island detection technique, we have impedance based island detection technique. Also we have rate of change of frequency, that is called as ROCOF in abbreviation, rate of change of frequency, and also we have rate of change of phase angle based technique and some signal processing based technique like artificial intelligence technique, or we have wavelets based technique and neural network based technique. So, those techniques are also used for island detection. Now, coming to this power quality monitoring based passive island detection technique, here what we do basically we measure the harmonic, the voltage or some ripples which are present inside the voltage. Based on that basically this technique is moving forward. Like let us say this particular block, we have measured the single phase RMS voltage at the PCC. PCC means the point of common coupling, and by measuring this RMS voltage at the PCC, then we will take the mean of this particular voltage. This is not our work, this work is basically cited in this particular paper. Due to the space lack, I have not kept all the data point here, that is voltage ripple based passive island detection technique for grid connected photovoltaic inverters. You can follow this particular paper where all the details are present, all details are present. By measuring this VRMS, we will take the mean of this particular voltage, that is 1 upon n, summation of this VRMS from I is equal to 0 to n. We will just average within a cycle, as already we have discussed that this n stands for number of samples per cycle, because in discrete domain we basically, because we have to basically process within the processor will understand the discrete domain data 0 1 status. Now, after taking this one cycle average of this particular VRMS, then we will send to another block where we will take the derivative of this particular RMS voltage and then the mean, and again we will take the integration, and finally again mean will take this integration value. If after getting this final D, if this D is greater than or equal to a certain threshold, then we will declare that yes, there is some islanding condition, or some islanding is present, otherwise it is no. If it is below the threshold, then there is no islanding. See, I just want to, this is one technique what we just we discussed based on this power quality monitoring technique, where we are just taking this voltage ripple and we are just taking the mean and average. So, those tasks are doing here, that in that case what happens, this threshold is a concern, because while deciding this threshold, so what could be the value, how to decide this threshold, you know. So, that is the major concern as far as the passive islanding detection is concerned. In every case almost next we will go for the rate of change of frequency. There also you see this frequency rate of change, the threshold is also one important concern. Now, this is how this particular technique goes. This is the voltage, this is VRMS, this is different blocks whatever the parameters, I mean the index, basically you can say A, B, C, D, and this is A, this is B, C, D, and based on those indices final trip signal is going to be declared, that this is islanding situation. Now, next one is impedance monitoring. The second one, the second passive element, the passive based technique, that is based on the impedance monitoring. See, if you see this particular picture, that this is our DC system voltage and this is a grid voltage and this is a grid impedance and this is a common coupling point and this is our load, RLC load. Let us say this particular mode of operation is grid connected mode, because this DG or the renewable energy is connected to the grid through this common coupling point. If we will measure at this point V and I and then the corresponding impedance V upon I, this impedance will be different, I mean it is written here. And if you just isolate this grid in this second figure, if you could see here this second figure, here the grid is not present, absent, grid is absent. So, again we will measure this V and I and the corresponding impedance. If we will measure, it will come like this. That means due to the change in impedance values and change in the impedance, then always we can declare whether this microgrid is in islanded mode or it is in grid connected mode. That is what the meaning of this impedance monitoring based technique. Now, we have a rate of change of frequency, you know at the point of common coupling this PCC we can always measure the frequency. In one of my class I have just discussed how to basically estimate the frequency from the phasors, or you can take the zero crossing technique. So, by measuring this frequency and after that we will just take the df by dt, or we can write it del f by del t. This particular index del f by del t is known as rate of change of frequency. Due to this rate of change of frequency also we can say whether this microgrid is connected to the main grid or it is disconnected from the main grid. Of course, here we have certain disadvantages, like in case of rate of change of frequency the threshold I mean is also one concern, and second point for zero power mismatch situation this rate of change of frequency does not work, because during zero power mismatch situation if your P load is equal to PDG, then there is no variation in the frequency, and that at that time this rate of change of frequency fails. Different type of studies, like by varying this inertia constant of the microgrid system, like by varying this Rx by X by R ratio, feeder length, different type of parameters are changed, tie lines, sampling frequency, this particular technique basically analyzed. A few figures are just presented here and we are taken from this particular article or this publication. We should always refer to the corresponding paper where this source basically this figures are taken. So, you can follow this particular paper. Due to the lack of space, we are just keeping the title and the journal name. Now, if you see here this is for different types of loads, like constant power model or constant current model or constant impedance model, this rate of change of frequency technique also vary. That is also one of the demerit. And if you would see here for deficient of power is a variation of this tripping time, excess power this is a tripping time, and this is a power imbalance in per unit, and this is the ROCF settings hours per second, and this is a critical power imbalance, at what percentage of power this particular technique is going to work fine, and below certain percentage of power mismatch this technique is not going to work. That is what the critical power point. And these are certain other issues, like as I said H stands for the inertia constant, and if you just vary this inertia constant like 1.5, 1.5, then also this critical power mismatch also percentage vary, and the setting of the ROCF relay also should be followed accordingly. And this is like L is the length of this feeder and the X by R ratio of the line or feeder in the present inside the circuit. So, if you vary those parameters also, this particular technique is also affected. Now, the drawback already I have discussed, requires a minimum power mismatch, this below 15% power mismatch, this ROCF rate of change of frequency does not work, that is one disadvantage. Second one, this performance can be affected type of loads and generator inertia constant. This particular technique is also affected due to this type of loads and generator inertia constant. Another technique is basically the rate of change of phase angle, that is ROCPA, that is the what here we do. I will just go directly to this flow diagram. Here the voltage and current signals are retrieved at the target DC location. After getting this voltage current signal, the phase angle between the voltage and current signals are calculated, and then the rate of change of phase angle difference are calculated. First, this is step 1, step 2, step 3. If this rate of change of the phase angle difference is greater than certain threshold, then yes, the islanding is present, otherwise there is no islanding. This is how this particular technique works. These are very easy techniques and these are very easy to be implemented, but however, if there is a relays power mismatch condition like a 0 power mismatch condition, or there is change in basically the network conditions, maybe these techniques are going to be affected. And the last one is the energy of rate of change of phase angle. What is the energy content within this change of phase angle? If we can track the energy within that, then also we can detect the islanding situation. Okay, so in this class we have discussed that what is islanding and why this islanding detection is very essential, and what are the different types of island detection techniques, and we have discussed passive island detection technique. The first one is basically the power quality monitoring based technique. Then we have discussed the impedance based technique, because during the islanding the impedance also varies, and next also we have discussed the angle based information like rate of change of angle or energy present inside the rate of change of angle. If we can trace those information or parameters or quantities, then we can detect whether the microgrid is connected to the main grid or it is disconnected from the main grid. Thank you.